Can you hear me in the back there, or do I need the microphone? You can't hear me? Do you hear me back there? Is that okay? Can I do it like this? Thanks. Okay, welcome to the second lesson in design of the wind turbine. Today we are going directly to the point, starting with airfoils. I'm working with the first design of the wind turbine, so it starts today. The turbine I'm going through will be your case. It's going to be the turbine you're going to work with. So today I will have the first guess or first evaluation of this, and that will be your first exercise as well. How to design this turbine. First of all, how many of you didn't come on Tuesday? Okay. All right. I don't have time to go through all of that one more time, so you have to go into Blackboard and have a look at the introduction we had there. It's all under the lecture notes, and you find the introduction of this course. It tells you what is going to happen during the course over the time. Please make a note of that you're going to be in groups. It's going to be an all examination, which is 50% of your grade, and the other 50% is the report of the project or group work you're doing. And we are going to divide you in groups on the way, and each group are going to design a wind turbine blade, just like this one. You're going to evaluate it, test it numerically, and then we're going to make a 3D drawing and then later machine it from a CNC machine. And then at the same time you're going to design a generator which fits to this turbine, and you're going to make that as well, test it, and then in the end we will have a competition in the wind tunnel, a competition between all of you groups, and the competition will be who has the highest efficiency of turbine and generator combined. They are doing the same thing at the Technical University in Berlin, and the best groups there are coming up here to compete with you guys. So on the top, you keep competing with each other, but we are also competing with TU Berlin. And the last 2 years, we have beaten them. 3 years ago, they took us. It will be quite intensive, the first part of these lectures. And then once we divide you in groups and you start to work with the project, it will be intensive group works, but not the lectures. So we divided it first in the theoretical part, and then the practical part, and in the end the competition. So it's a different course than you ever had before. The lecture plan is shown not on its learning anymore, but on Blackboard. Follow the lecture plan, and on the lecture plan I show what's going to be taught and what references we have to the curriculum. And please prepare yourself before you come, because a lot of the things we are teaching is quite abstract, especially for you guys from Emil, third year. A lot of these things are new for you guys, so prepare yourself before you're coming to the class. It goes for all of you actually. And sometimes I get the feedback that I'm going too fast ahead with the teaching. But every time I ask if they could prepare themselves before they came, I don't get an answer. So please do that. It will be fast. And it will be fun. I promise you that. But make sure you see what's going on. The last change on the lecture plan now was that I have to cancel the 5th of September. It's not going to be any lecture on that day. It means that everything is shifted downwards. So today I'm going to introduce you to the flow around an airfoil, and then try to connect that to the turbine, this one. And in the end, we are going to design, or we're going to go through the design procedure of a simplified blade for the turbine. Because anything we are doing from now is based on this first design evaluation. It will be your first turbine, actually. And on the way, we will change it because we will optimize it based on theoretical input from us. Any questions?
Can we try with the microphone, because I think it will be better.
All right, I'll try. Another thing, it will be, we are filming the lectures because there is a course crash for the students coming from mechanical engineering. So we are opening the possibility for them to follow the lectures. Let's see if this works. Hello? 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 Okay, let's try. The movies we are filming will be announced on Blackboard, and you will find it on a YouTube channel, I think, from NTNU. Okay. And I'm not looking forward to see myself on the movie, to be honest. Airfoil theory is the easiest way to start to relate the airfoil or to have some kind of physical background is to start to think about the airfoil we're using on airplanes. All you guys have been, at some point, have tried it, and we will try to first link it to that, to the airport, to the airplane, and then later on try to link it to the rotational turbine. So let's start with the aerodynamics. First of all, a blade, a wing of an airplane is made out of many different airfoils. This is typically one airfoil. But if you see on the airfoil line of a wing of an airplane, you have different airfoils and different sizes of the airfoils. And that will be the same for the turbine. We see different, they have different shapes and they have different size. And this is, I'm going to go through how that is, how and why we are doing this. If you look at different type of use of airfoils, you find different airfoils. And for some airfoils you find information, for some you don't, because it's classified. We will give you airfoils and we will give you all the data for the airfoils in this class. But you see different types of airfoils for sailplane, for example, or powered aircraft or small wind turbines. And they have different shapes. And it all comes down to how the characteristics is based on lift and drag. Drag being friction resistance. And we will go through those things now, try to see what to focus on and how these things are defined. How many of you have had airfoil theory before? Any of you? Okay, but you are not students from NTNU, are you? You are? Okay. Okay, then this class will be maybe a little bit repetition for you guys. Let's take a look at the airfoil. It has a characteristic shape. Kind of flat on the bottom and then curved on top. And each airfoil, different airfoils have different curvature. If you look at birds, they are also using this kind of airfoils, different shapes for all birds. But I want you to just to try to understand the physics. I'm simplifying a concept. Let's assume that two air particles, starting from the leading edge of the blade in the front. So we're calling this point the leading edge. And they are going, one of them are going at the bottom, following the bottom line, and the other one is following the upper line of the shape of the blade. And let's assume they are meeting at the trailing edge at the same time. It's not 100% true, but it's close. And we are also assuming that these two particles have the same amount of energy. And the energy we find here is either kinetic or pressure. That's the two energy things we are looking at. So, the upper one, he has a longer distance to go. So he has to increase the velocity in order to meet the other one at the trailing edge at the same time. Meaning, he has a higher kinetic energy, which means that the pressure has been lowered compared to the one that is moving along the lower shape of the blade. So that means this blade will have a higher pressure at the bottom than at the top. And that's the whole trick. So you will find a pressure distribution could be like this. And that sum of those, the summation of the pressure on this blade or airfoil will give you a lift. That's a force. One thing you have to bear in mind, that force is always acting normal to the incoming wind velocity. So no matter how the blade is actually located, the lift force is acting normal to the wind velocity. And then we have the drag. The drag is mainly coming from friction over the surface. It looks like the drag is about the same as the lift, but that's not the case. It's something around 100 times lower than the lift force. So it's a different, two very different numbers of those forces. Let's take a look at the typical pressure distribution along the surface of the blade. If you look up there, you see the leading edge is denoted 0, and then at the end of the x-axis, so to say, it would be the trailing edge, and the pressure along the upper surface is now in the vertical axis, and the pressure is negative upwards and positive downwards. You see at the leading edge, at the top of the blade, we have a very high negative value, while you have a very high positive value at the lower end here. So in this case, the first part of the airfoil is giving a lot of lift, while you see the difference between upper and lower part is getting smaller and smaller while you're moving towards the trailing edge. This is typical for most airfoils, that you have a lot of lift in the coming from the first part of the airfoil. But different for any airfoil geometry. Let's define a few things. First of all, we need to define the chord line, which is a straight line from leading edge to trailing edge. And the chord length is according to the length of that chord line. This is something we need to bear in mind when we are using angle of attack, because there will be an angle of attack to the airfoil from the wind velocity. So the angle between the wind velocity and the chord line is defined as the angle of attack. And the higher the angle of attack, the more lift you will have, and at one point we will have more drag as well. But you can't have too high an angle of attack. Let's take a look at this. Here you see we are defining the lift force, which is simply the density of the air multiplied by the wind velocity far upstream of the blade, squared, divided by 2. And then you multiply that by a lift coefficient. And then this chord length and the depth is an area. And that area, this is often a confusion, that area is simply the area of the blade itself. So chord length is this length from leading edge to trailing edge, while the depth is this height. Later on you will work with blade element, and each of these blade element will have a depth. So you have a chord length and a depth. If you look at the equation, this part is simply a pressure, and this part is an area. Pressure multiplied by an area is a force. And then you have this CL, which is an empirical coordinate, different for each blade. The CL, lift coefficient, is a function of the angle of attack. And if you look at the graph to the right, you will see that based on angles of attack from -5 to 25 degrees, you will have different lift coefficient varying from 0 up to almost 1.7. But at one point it stops. It's not growing anymore, it's actually going down. This is when the flow is not following the shape of the blade anymore, and we have separation, we call it stall, and then we'll start to lose the lift of the blade. This means that when we design a wind turbine or a wing of an airplane, we need to stay away from that region. We need to know that we are within, in this case, -5 to about 10 to 15 degrees angle of attack. Next time you go into an airplane, take a look at the nose, on the side of the nose. There is a small wing there hanging on the side, which is movable. And that is actually telling the pilot what angle of attack he has on the airplane. At one point, that will give him a warning if the angle of attack is too high. It's called a stall warning. All airplanes has that kind of equipment. Each blade has its pressure distribution and its CL, and this is just an example of a NACA profile, data from NACA that shows what kind of lift and drag, or in this case, pressure distribution at 0 degrees angle of attack and at 10 degrees angle of attack. The NACA profiles is something that is available for all of us, and if you go on the web, you can actually search it and find that information yourself. Just different examples. A few other things we need to define. We told you about the chord length. We also need to talk about the camber line. And the camber line is different than the chord line. The chord line is simply a straight line, while the camber line is the middle line, also in the middle of the upper and lower surface. So the red line there on this one is the camber line. I guess you have seen on the airplanes when you're landing or taking off, you see that they have a flap that is coming on, off, or they're changing actually the airfoil by adding something at the trailing edge of the blade. And that changes the camber line quite a lot. It becomes a lot more bowed. That's because during takeoff and landing, they need a lot more lift, and they have at relatively low air speeds. So they and the drag is relatively low because of the airspeed is low. But when they are up and running and then going with full speed, then that airfoil is not needed anymore because it will give you too much lift and too much drag. So that's why they're going back to the original airplane airfoil. The thickness of the blade is simply defined as the height between upper and lower part. The angle of attack I have talked about. The drag force and lift force is something we need to define. And again, note that the lift force is always normal to the wind velocity. You see it here. Wind is coming up like that, and the lift force is normal to that line. Drag is perpendicular to it. We are going to calculate those two forces for our geometry later on. Let's see, we have defined this. Here we have another line of lift relative to the angle of attack. The drag is defined exactly the same way. The only difference is that now we are changing the lift coefficient with the drag coefficient. So these numbers on that side, the pressure we're talking about and the area we are talking about, is exactly the same. First time I saw that, it felt a little bit strange because then the friction is not relative to the whole cross-section area, but these are empirical relations, and this is the way they have defined lift and drag. So it's a kind of a definition we need to accept. If you look at the drag coefficient relative to the angle of attack, you see that the numbers are a lot smaller. Here we are talking about something from 0.04 up to 0.05 0.004 up to 0.02. Remember, the lift coefficient was from 0 to 1.75. So it's a totally different scale. So that means that the drag force is a lot smaller. But to simplify the way of thinking, or the way of having it, you're using the same equation, exactly the same equation. You're only changing the coefficient. That's the difference. Okay, now we are. Now that we had defined these numbers, I'm ready to go to the wind turbine. Because we are the blade, the wind velocity on a wind turbine is not working towards the wind velocity. We are talking about a relative velocity here. We are rotating and the wind velocity will be changing. Something that was hard for me to understand the first time I saw this was that the turbine blade, the tip of the blade here, is actually rotating 5 to 10 times faster than the wind velocity. How is that possible? I will try to explain that now. First of all, we need to define a few things. Okay, we have a rotational velocity of the turbine, or a peripheral velocity, meaning the velocity of the tip. Let's assume that we are on the tip now. And that is tangential to the rotation of the turbine. The wind velocity is normal to the shape or to the surface of the turbine. So we have the peripheral velocity, which is a tangent to the rotation, and the wind is coming normal to that line. So we have two velocity components normal to each other. The relative velocity is simply the vector sum of these two. So imagine, from now on I would like you to imagine that you're sitting on the blade and you are trying to understand where the wind is coming from. First of all, if you are sitting on the blade here and the turbine blade is moving upwards, you're feeling that the wind, because of the rotation, the wind is coming directly towards you. And the wind velocity, the wind from the wind that is blowing is coming normal to you, so of course. So let's take a look at the blade. Now, let's assume I am the wind turbine and you're sitting there. The blade is moving upwards, but because of the movement you are feeling velocity r times omega, the peripheral velocity, is coming directly towards you. So because of the rotation, that wind component is coming towards the leading edge of the blade. And then, of course, the real wind is coming normal to the surface of the rotation. The relative velocity will be just the diagonal of this triangle. You see? So it means that if I'm sitting here, going upwards, the wind, I can feel that the relative velocity of the wind I'm feeling is coming from somewhere up there. That is the sum of these components. And here you can see that the lift force is normal to the relative velocity, and the drag force is is just tangential to, or in the same direction as the wind velocity, the relative wind velocity. All right, what makes this turbine to go around is actually the sum of these two forces acting in the vertical direction. You see, both lift and drag has a common component in vertical direction. And it's those two components which is actually making the turbine going around. And both of them have a component in that direction, trying to push the whole turbine backwards. We call that the thrust force. So we have one force trying to push it backwards, and there is one force making the turbine go around. So we define those two directions of the forces to be thrust and torque. I think I misspelled thrust here. But for us, it's all about finding out how much torque we have. Just to be a little bit ahead of what we are talking about now, the output power from this turbine is defined by the torque multiplied by, we're using, in this case, omega. And omega is the rotational velocity in radians per second of the turbine. So how fast it is actually rotating. I guess you all are familiar with the rotation per minute, but in this case we are sticking to SI units. We have to use angular velocity, so radians per second. So it's the same thing. So the torque we have from each of the blade element we are going to design, multiplied by the angular velocity of the turbine, gives us the power output. And that's where we are heading. This is where we are heading. So let's take a look at this velocity triangle at different radiuses of the turbine. So far I have only been speaking about the tip. But if you look at those components, the question is will they be the same for all radiuses? No, this R times omega will be different because the radius is changing. So if you are sitting at different radiuses, you have a different peripheral velocity. Let's assume now that you want to have the same angle of attack for all blade elements on the turbine. And you have that velocity triangle, this triangle at the inner part of the turbine, and you have this velocity triangle at the outer part of the turbine. That means in order to have the same angle of attack, you need to twist the blade. And that's why you find the propeller blade and the turbine blade twisted. You see it here from one of the blades from last year. You see it here from the blade elements that has been calculated from one group. You see it there. You see it on the propeller on any airplane. You see it on the propeller of a ship and things like that. That's also a thing to notice, is that the theory we are talking about here can also be applied to other things, just like propellers and fans. And if it can be applied to a ship moving across, they are utilizing the thrust force, of course, because that is pushing the ship. All right, let's take a look at the forces we have. As I said, we have one force forcing the blade to move around, and we have one force, the thrust force, trying to push it backwards. We have also a force on each blade. If I'm the blade, and when you twist the blade, there will be a force around the twist or the length of the blade. You will also have a torque there. So there are many things to handle. In this class, we are not going to go in depth about that. We are only going to talk about the lift and drag force and the torque and thrust force of a blade, which is not going to be pitched at all. But I will later talk about the other components as well, just to know, so that you know that there are other challenges as well when you design a turbine. There are a few things you need to understand, and you need to see as well. The forces scale linear with the chord length, so if you double the chord length, then the force is doubled. It's quite simple to see that here. You have a linear correlation with the chord length. For a given angle of attack, the lift force increases. You need the definition, you need all the data from each and one of the blade or your geometry in order to find and define those lift and drag coefficients. Thick airfoils is of course, they have a lot more drag than the other ones. We will have to define a minimum thickness for your airfoils, because we have a limit on the CNC machines. If you go below, I think it's 1 millimeter at the trailing edge here, you will have trouble with the machine, which is going to machine it out for you. Laminar and turbulent flow. I guess most of you have defined what's the difference. If not, you need to go back and have a look, or go into the basic fluid mechanics to find out what's the difference. But we are assuming turbulent flow over these blades. Always. Just a side note, when we defined, or here at NTNU, we designed a turbine which was going to be utilized for tidal flows. It looked more or less exactly like this one, 3-bladed turbine for water velocities of up to 2 meters per second. We designed it here, and we tested it in the wind tunnel, and we almost never came into turbulent flow for that turbine. It never gave us any of the results we were expecting, because all of the calculations we had done on beforehand was based on these coefficients, which was based on turbulent flow. So laminar flow is a different story. On a surface, you will always have a laminar flow in the start of if you have flow coming over a surface, there will always be laminar flow in the start. So let's look at the surface of this blade. When the flow is going like this, the first part here will be laminar, and at one point you will go from laminar to turbulent flow. This is what we call the tripping point. And for some turbines you can actually define that point by actually adding something on the surface. So for the turbine we were using in the tidal turbine, we actually added a roughness here, just sandpaper actually, fine sandpaper, and we tripped the turbulence. And it came into the normal operation. And for some turbines and some airplanes you see it as well on the blades. And that is also one of the big uncertainties when we go into the wind tunnel. You guys will also be close to the laminar range of the turbine. So actually if you're spending too much time trying to polish it too much, that transition point might be on a different place than expected. And that will actually lower the efficiency. Okay, let's define stall. There is a boundary layer on the surface of the blade. And of course we would like the wind velocity to follow the shape of the blade all the way to the trailing edge. Remember now that the pressure on the top of the blade is lower than the surrounding atmospheric pressure. Normally the wind would blow from the high pressure to the low pressure. This is doing the opposite. And at one point it will try to do the opposite, of course. So if you look at the upper one, that's what we expect to have. We have a nice boundary layer which is acting all the length of the blade upper surface. But at some point at the trailing edge you will have a boundary layer starting to fail, which means you have a separation on the surface. And it will start at the trailing edge and it will move forward. If you go to YouTube, you will find a lot of different movies showing this. But you see here for the lower part, it's like you get separation over the whole, more or less the whole area at one point. And that's when we define stall condition. Are any of you guys pilots? Have you certificate on airplanes? I guess many of you have friends who have a certificate. I know that when you are taking a certificate for a small airplane, you should test to stall your airplane during flight. And it's quite scary actually, because you lose everything. You just fly and you change the angle of attack until you have no lift and you just fall. And the airplane is stable, so you will get into normal condition quite soon, but still it's something you need to understand what's going on and when it's happening for your airplane. So if you are out there with a small airplane once, ask your friend or the pilot to stall the airplane. It's quite an experience, I can tell you that. Another thing that some of you, I want you to consider to include into your calculations are the tip losses. If you have an airfoil and you have a pressure difference between upper and lower surface, tip, the air might take the shortcut to the lower, from the highest pressure to the lower pressure. And that's the tip loss. All airfoils has this kind of tip loss. That's why you see this, the new wings on airplanes, they have these winglets. You find them on wind turbines as well these days. This airplane has a winglet, and that's why you see that the trailing edge or the vortex coming from that tip is small compared to the tip of the flaps, which is coming at the trailing edge. Because the flaps looks like this, and it's coming here. And you see to the right, that's the tip vortex from a two-bladed turbine. Okay, how many of you have calculated the Betz limit and been through that definition of Betz limit? 1, 2. Okay, not too many of you guys. We are going to prove or define a limit for the efficiency of the turbine. It is defined to be 59%, and that's the maximum you can get. And I'll teach that next lesson, next lecture. But to give you a kind of a physical understanding of it is quite simple in my opinion. First of all, the wind turbine is utilizing the kinetic energy of the wind. 100% efficiency would mean that the velocity kinetic energy at the downstream end of the turbine would be 0. That's not possible. The air has to go away. So that's the main part of the reason why it's only 59%. Another typical loss would be the fact that some of the air has the possibility to go outside the blade. And the turbine surface is actually, it creates a higher pressure in this area. So of course, if the wind has the possibility to go outside, some of it will do that. So those are the two main components, which is the reason why we can't have 100% efficiency on a wind turbine. State-of-the-art wind turbine today would be 45 to 48% turbine and generator efficiency total. Students from this class designed and tested turbines between 43 and 44% combined efficiency. So you will, I guess the best of you guys will be close to state of the art, which is on the commercial market. And that's very nice to see. I'm going to just introduce some kind of thinking for you guys before I go to the next, before we take a break. The rotating disk theory is something I'm going to teach next time. We are assuming, in this case, that the whole turbine area, the rotational area here, is just a disk. And we can look at it like that. Because we are extracting energy from the whole cross-section area. And then we are introducing the rotation to the wind. Believe it or not, the wind at the downstream end of the turbine is rotating. So even though the wind is just having one velocity here, it will rotate at the downstream end of the turbine. That's what we call this, we call it the turbine wake. And that rotation will always be opposite to the direction of the rotation. We will see it later on that you have to have a component in that direction in order to extract energy from the air. Later on, we're going to introduce the blade elementum method. And when we do that, we introduce two more components to it. And those are these induction factors. Induction factor means that we need to change these velocity triangles or velocities at the turbine itself is changing. It's quite understandable to think, or it's logical to think that the wind velocity when it approaches the turbine will slow down a little bit because this turbine surface has a higher pressure. So we have an induction factor in the actual direction, which is actually reducing the velocity we have here. And then that's the A without a node. And then we have the rotational induction factor, which is where we are saying that since there is no rotation of the turbine at the upstream end, there will be one while you're passing the turbine. So we need to introduce a kind of rotational velocity to the system. Okay, let's take a break.
Kan du stille spørsmålet?
Ja.